A ball rolls across a 50-meter surface for 5 seconds before coming to rest. Calculate the acceleration of the ball. I'm told how far the ball rolls, which is 50 meters, the amount of time, which is 5 seconds, and at the end of its motion, it comes to rest. We're looking to solve for the acceleration of the ball throughout that period of time. The table where you identify and record variables can be organized like this: delta x, vi, vf, a, t. Delta x, we're told, is 50 meters. It's the horizontal displacement. The next thing we're told is the amount of time, so that's 5 seconds. The ball comes to a rest at the end of its motion, which is 0 meters per second. And we're solving for the acceleration, so I'll put a question mark. There is one variable that is not mentioned, and the fact that it's not mentioned is important. We're going to use that to help us determine which equation we want to use to solve. The equation we want to use to solve should contain delta x, vf, a, and t, and it should only contain those variables. If we had an equation that also contained vi, then we would end up with 2 unknowns. So the way I do it is I just go through and look at each one. The first equation, I can see that it contains vi right there. The second equation, I see vi right there. The third, vi is right there. The fourth one, I don't see the initial velocity. The fifth one, I see it right there. So not good, not good, not good, not good. The equation that we want to use is this one. Now that we have it selected, we're going to write it down. I think it's really helpful to put parentheses around the products so that you don't accidentally combine terms before you're supposed to. Also, I should note I'm using a capital A because my lowercase a's look like 9s and it can get confusing. Once we have our equation written out, we can plug in our givens. Delta x is 50. I'm not going to include units just because it's a little bit easier to follow without them, at least at the beginning. The f is 0. That's going to be multiplied by t, which is 5, minus 1/2 a times 5 squared. I can simplify this, so 50, 0 times 5 is just 0, minus, and I'm going to do this in every single step I can, so still 1/2 times a, and now 5 squared is 25. I'm just going to get rid of the 0 and just make this negative 1/2 times 25 is 12.5. And that's still being multiplied by a. Since we're solving for a, we want to isolate it. To do that, we need to get rid of the negative 12.5. Since negative 12.5 are being multiplied together right now, to isolate it, or to move the 12.5 to the other side, we need to do the opposite of multiplication, which is division. That allows me to cancel out the negative 12.5 on the right side of the equation, and 50 divided by negative 12.5 is negative 4. And bring down my equal sign, and what's left over on the right is just a. So finally, the acceleration is equal to negative 4. And if we had kept units in our calculation, we would end up with the units of meters per seconds squared. The fact that our ball is moving to the right and it slows down, our acceleration should be negative. So that's why it is. It's slowing down. And that is our final answer. A ball is dropped from a cliff 50 meters above the ground. Calculate how long it takes to hit the ground. We're told the cliff is 50 meters and we want to know how long it takes. So the variable that we are given directly is delta y. And for vertical motion problems, I'm going to define the downward direction to be negative. So since the ball is being dropped, it's like its initial position was at 50 meters, its final position was 0 meters, and if displacement is final position, or YF minus initial position, YI, it's kind of like 0 minus 50, which is negative 50. So you can think about it that way, or you can just remember the downward direction is negative. We also know that we're solving for time, so I'll put a question mark there. And at first glance, you might think this is all you have. But it's really important to remember that for vertical motion problems, there are some things that you just have to know. So the initial velocity, whenever something is dropped, not thrown, but dropped, you can assume the initial velocity is 0 meters per second. What's not 0 meters per second is the final velocity. So we don't know what the final velocity is going to be. I tried to draw it in the picture, but I'm going to point it out. So initially, the ball isn't moving so fast. It's starting from 0 meters per second, so stationary. You let go, then it's going to get faster and faster and faster until it hits the ground. When it hits the ground, that is when it's going the fastest. We also should know that the acceleration is the acceleration due to gravity, and on planet Earth, that is approximately downward, so negative, 9.81 meters per second squared. And finally, the final velocity is not mentioned. So using the same technique that we used previously, we're going to look through the different equations and figure out what is the one equation that does not contain, in this case, VF. We can't use the first one because I see VF right there. We can't use the second one because VF is right there. Can't use the third, can't use the fourth, which leaves us with the final equation, delta y equals VI times t plus 1/2 AT squared. Now we can plug in our values, delta y, -50, and I'm going to leave units out for now because it makes it a little cleaner. It's actually not the best practice, but when we're learning, I think it makes it easier to follow. VI, 0 times time, which is what we want to know. Which, if 0 times t, we know it's going to be 0. If that was the only t in our equation, this would not be very helpful because we want to solve for t. But luckily, we still have 1/2 times 9.81. And I'll put the multiplication symbol, times t squared. -50 equals, well, 0 times t is just 0, so I'll just continue on. 1/2 times 9.81. I'm going to round to, whoops, negative 4.9. And that's still being multiplied by t squared. Our next step would be to isolate t. And so since -4.9 and t squared are being multiplied together, I want to do the opposite of that. So divide by -4.9, divide by -4.9. That cancels out. And I get 10.2, and that is equal to t squared. So is that our answer? No. I'm solving for t. I am not solving for t squared. So we have one final step. To get rid of t squared, to get rid of the square, we have to do the opposite, which is the square root. And the square root of 10.2 is around 3.19. Leaving finally our answer, t is equal to 3.19 seconds.